Okay, good morning, good afternoon, good evening. Welcome back to another Coding Notes Every Day Until I Get a Job. This is day 139. Apologies, haven't been updating in a while, but here we are, back again. I think I want to try to continue the CS50, finish the DSA. I need to really, what do you do a lot of revision and probably a lot of relearning. I don't know why this site won't load. Okay. Why is it not working? Why is it not loading? Okay, let's see. No, this is not the CS50 that we usually use. Mm-hmm. Is it this one? No, okay. Um, why is it not, is it something wrong? cs50.harvard.edu. So yeah, basically let's just proceed, I guess, continue. So see, we can just make this bigger. It's okay. It's been a while since we used npm. I know we should update the config and everything. I haven't really played around again with the uh, config because I think the 0.11 update, they said that we don't need LSP anymore. Like we don't need like plugins. Like I was using Mason. Then again with that we don't really need that anymore, I guess. Or, I don't know. And I think my wrists are really starting to get hurt this past weeks. Okay, this site is not loading. I'm gonna try to open a different browser. I don't know why that doesn't work. Is it because I'm not using a correct one? Can I use this instead, maybe? Because we don't really track any progress anyway. We're just there to learn and see the content. Okay. Okay, there. Someone like TLS50 blocked the IP or something. Okay, this is not cool. I don't know why this doesn't work. I don't want the edX one, you know, I just want a normal video. Okay, you know what? We can just go to their YouTube, you know. I think we can just go to the YouTube and if I remember, but the notes, man, I really like the notes and how it's all just structured and everything set up. Um, okay, this website is not loading. Is it something wrong? If can I open it with my phone? cs50.harvard. Yeah, that is odd. Why is it not working? Is it like updating some certain thing? Wait, yeah, let me change the light as well. That is much brighter. Okay, I have no idea why that doesn't work. I think we can just go to the YouTube and just proceed from there. I have no idea why it doesn't work, so that is not cool. Okay.
All right, so we are back, and I admit that like the code that we just wrote to build a link list absolutely complicated, but
Yeah, very
it's
complicated.
intuitive. Like
Definitely don't
you
know how to.
stitch things together in memory and build more interesting structures. And so here on out today, let me propose that if you're at least on board with this idea, that with some kind of complicated code, but with the data structures in memory as you see fit. Let's just take for granted then that we could implement the underlying implementation details for the following alternative structures. And indeed, let's see if now we can draw some
Talking about trees. Okay.
really appealing now in retrospect because
Sup? Hello, Mookie. Welcome to the stream. Hello, hello. How are you?
arrays with this idea of linked list, or at least more generally stitching things together, because maybe we can kind of get the best of both worlds. Because arrays, recall, give us contiguousness. That means we can potentially do binary search, especially if the data is already sorted. But of course, we paint ourselves into a corner with arrays because they might not be big enough for future data. So then we introduce linked lists, and linked lists are wonderfully dynamic. We can make use very creatively of memory, but with the catch with linked lists, of course, is that we're using extra space. The code got more complicated, so it's sort of the seesaw going back and forth.
Exactly. I am currently, I know it's probably not really like the best answer, but it's more like, no, I mean, like, I know it might sound odd that I'm learning basic DSA, but the role that I want is more on the UI UX design and front end roles. But I had an interview and I failed, so this is sort of like a revenge arc, so to speak, like revenge training arc. But yeah, I'm mostly looking for the front end or UI UX or design stuff, but I for some reason got interested in learning the other as well, so the whole full stack. So basically here I am learning the DSA.
Structure in computing is that known as a tree, sort of like a family tree, which we've mentioned before, where you sort of have this upside down tree structure where a root is so-called up here, and then you might have children and grandchildren and so forth. So it sort of grows on the screen top to bottom, much like a real tree sort of grows.
Yeah, redemption arc, the training arc basically. So yeah, this is what I'm doing. I felt terrible that I wasn't able to answer, or I don't have really a good answer during the interview. I wasn't prepared, I wasn't ready, and kind of got punched in the face by that. Okay, this is actually so fucking serious. I don't know anything, and I couldn't really answer a simple question, and I sat there staring at the screen after the interview, and I was like, oh fuck, man, I really need to start being serious. So at least this is my attempt at it.
Is pretty much one-dimensional. Like an array is just left to right, and even though linked lists
so yeah,
kind of go up and
this
down
is where we are today.
At the end of the day, it's still a left to right linear or one-dimensional data structure. So what if we start to use a second axis, so to speak? Well, it turns out there's specifically a type of tree in the world called a binary search tree, which is this two-dimensional tree-like structure that you can actually perform binary search on. Because we did pay a price too with linked lists, you can't do binary search on them. Even though you get all the upsides we discussed, the flexibility, the dynamism, why can you not do binary search on linked lists, might you think? Based on how we've drawn them thus far, yeah. Exactly, because they're this long string-like data structure that you can't just go backwards on. I said, like, unless it's a doubly linked list, you can't go left and right, and there's no mechanism for jumping to the middle, right? No matter if you have arrows going left or right, the only way to get to the middle is to sort of traverse, frankly, the whole thing, figure out how long it is, then do it again 50% as much time to get to the middle. So that doesn't seem like very instant, constant time access. So long story short, on linked lists, you cannot do binary search, which means the best we're really going to do for most of those operations is big O of n, unless we do the whole prepending thing and achieve some constant time access, but that would seem to get us in trouble by slowing down other operations eventually. All right, so what is a binary search tree? Well, here's an array, as we've seen in the past, this one with 7 doors, if you will.
I think it was 2 weeks. No, it was like a month ago.
This a little bit, so as to highlight where the middle is.
Around a month ago.
The middle of the middles are, and where the middles of the middles of the middles are in this case. So we now have 3 different colors on the screen here, whereby the 4 was the first middle, the 2 and the 6 were potentially the left middle or the right middle, and then the 1, the 3, the 5, the 7 are similarly in the middle, depending on whether you go left or right. But I'm going to draw it this way because let me propose that this is an array at the moment, so we do have the ability to do binary search, but we don't have the ability to grow or let alone shrink this structure. But suppose that's a goal. We'd like this thing to be able to grow and grow and grow and maybe shrink over time. Well, what if I redraw this array by using some pointers in memory, kind of like this? I've just kind of exploded it vertically so that you can see more clearly that we actually kind of do have like a family tree-like structure here. If we think of 4 as the root, and 2 and 6 as the children of that root, and 1, 3, 5, and 7 as the grandchildren of that root, so to speak. And in fact, if I draw some lines to make this more clear, I indeed think that's what we have. Now, at the moment, I've drawn things more abstractly. I'm just using simple squares now. I'm not drawing rectangles with numbers and pointers, but these arrows do imply that each of these nodes containing a number also contains not even one, but 2 pointers now. And in fact, that's where we get our second dimension. Suppose that each of these nodes, these containers for data, contain not just a single pointer, but 2 pointers, one for a left child, so to speak, one for a right child, so to speak. That would seem to give us the ability to build this thing up sort of two-dimensionally in memory. And what's the implication of having built this up in this way? Well, how much time does it take to search this data structure now? Well, I can still do binary search even though pointers are involved, because so long as you keep track of the root of the tree always, with like one special pointer called root by convention, well, I can decide whether the number 5 is in this tree by starting at the root, and I know that 5 is obviously larger, so I can follow, instead of jumping to the middle of the middle, I can literally just follow the arrow to the right child. Now I know 5 is less than 6, so I can just follow the arrow to the left child, and voila, there is the number 5. Or maybe it's a dead end, in which case 5 might not be there, but I can implement binary search.
Now, at what day you think you can crack a job? I'm still applying, although not daily, but I'll try to apply maybe like, I think I did like 15 per week, like 15 application per weeks now. I'm probably gonna increase the amount, but yeah. Yeah, besides this, I also do like other side projects, like that is more full stack, that some part that I cannot really stream or share, but I'm also still doing other side projects as well. And to be honest, yeah, most of the time right now is just I got a part-time work job, but it's not a developer job, so that doesn't count. That's why this series is continuing, even though the title has changed multiple times. But yeah, I hope by the I'll try to I'm aiming below 200, but judging by the economy and all the other factors, it could be quite some times before that. But I really hope that below the 200 we can definitely do it, or at least try. Okay, so we'll see how it goes.
Search, not even with doing arithmetic like in the case of arrays, I can just literally follow these arrows so long as I built the data structure in this way. Now, how could I do this in code? Well, here, we're not going to write actual code with VS Code, but here is how I might implement a data structure for this in memory. Well, I could redefine the notion of a node as being no longer a number and a single pointer to a next field. This was how we defined earlier a node for a linked list. But let's reuse the notion of a node as just a container for data, and instead build a node for a binary search tree, as we've just shown. Let me make a little more room vertically there, and let me propose that a node in a binary search tree that looks like the colorful picture should have one pointer called left, another pointer called right, that are going to literally point to other such nodes. And if it's null, that just means you're a leaf of the tree, which means you're at the very bottommost level with no additional children. So this is indeed exactly how you could build, using the same building blocks as before break, a more complicated two-dimensional structure in memory, but gain back the ability to use binary search, which means now our running times are back in play, such that a data structure like this can finally give us, big O of log n running time. But what's the downside? If I'm now pitching this as like you want binary search trees now instead of just arrays or just linked lists, because you get back binary search, but you still have the dynamism, the growability of a linked list, what's the
Is it
downside?
the amount of memory? Because it took an extra additional. Okay,
It takes
yeah,
up more memory because I
yeah,
have not one but 2 pointers
yeah.
now for
Okay.
every node, which might be problematic, might not. It's really a design decision ultimately. But I will stipulate that this is very common design when you do have a structure in memory where you do want this kind of ordering to it, and you don't want to waste time, like we saw with arrays, constantly copying or moving things back and forth around in memory. What's nice, too, about two-dimensional data structures like the binary search tree, and binary search tree just means, to be clear, that you can do binary search on it. Why? It means that every node's left child is less than the root, and every node's right child is greater than the root, or equal to. Left child, clear that you can do binary search on it. Why? It means that every node's left child is less than the root, and every node's right child greater than the root, or equal to technically would be allowed as well. And that's, in fact, a recursive definition, because why I can apply it here. The left child of this node is smaller, the right child of this node is smaller, the left child of this node is smaller, the right child, sorry, meant to say larger before. The left child
Yeah,
of this node is
okay.
smaller,
The
the
right
right child
child.
of this node is larger. So that is true for every node, including the leaves, that just happens to have no children. So it certainly doesn't violate that same definition. So anytime you have this sort of recursive structure, just like the Mario bricks a while back, so can you use recursion in code. So I'm going to show code, but we're not going to write code, we're not going to run code, but here's code using recursion to search a binary search tree. So think of this as the implementation of binary search, but on a two-dimensional tree structure instead of an array. If you pass
Check DSA playlist driver. Okay. Is it on YouTube? This one? Oh, nice. Okay. But he's doing it in C++ now. I was actually trying to look for a DSA, but in JavaScript. I think I found it. Like, because I kind of really want to fight JavaScript. Like, yeah, I think it's either one. Yeah, I think it's this one by Hussein. Yeah, but or by Codevolution. So I think let's just, yeah. Let's start with the basic first.
So a pointer to the so-called root, and you give me a number you're looking for. Here is how I could search a two-dimensional binary search tree that someone else has already built. I can first pluck off the easy base case. If the tree you've handed me is null, well, I'm just going to return false. Obviously, the number is not in this tree because there is no tree. That's easy. Else, if the number I'm looking for is less than the current node's own number, think about that root. So it might have
Yeah. Okay, this arrow syntax is still, how would I say it? Like, I'm still not very familiar with it. Because if I remember correctly from my notes, the tree arrow number just meant that it's I forgot what is it about. It's basically that since the tree is the node itself, it's basically the tree dot number, because the tree is the data, because tree is the variable name of the node, and inside of the node, which is we set up with the type def, there is a variable of number, basically just like that. But yeah, it's still just haven't registered to my brain yet. So yeah, I started the DSA, I think it's a few weeks ago with the CS50, but I haven't really practiced much yet, and I'm kind of want to just do all the theory first and then practice. But yeah, we'll see how that goes.
That's like the number 4. Think of that as the starting point. So if the number we're looking for is less than the root's number, well then, let's go ahead and search the left subtree for that same number. Else, if the number we're looking for is greater than the current node's number, well, search the right subtree for that same number. Else, final case, if the number you're looking for equals the number in the tree, the node that you've been handed, then just immediately return true, you found it. And this is an unnecessary piece of logic. That can just be our else condition there. So just like the phone book back in week 0, where we were dividing and conquering by splitting the thing again and again and
Log
again,
of n,
that's literally
right?
what we're doing here. Even though I'm using search here and here in my search function, aka writing a recursive function, every tree I'm passing in is getting smaller and smaller and smaller. So if we rewind to the picture, it's like starting here and then deciding, oh, wait a minute, I'm looking
Yeah.
something over
It's just
here.
that the professor really has like a good slide showing that, okay, basically it's just like, because the tree is that type def node, and inside of it there is like number and then the pointer, the arrow means that the tree it's like referring to that number of that tree. Like I constantly needs to like, okay, like going in one by one, because sometimes I just like, what the fuck is this? Yeah, but yeah, it's basically like the number that belongs to that tree, right? To that node. Yeah. Yes, that's what I, yeah, like that yeah. Yeah, correct. Yeah,
Kind of snip that subtree
that is
and
correct.
focus only on this one, and then snip, and you're essentially halving the size of the tree each time, just like we were halving the size of the phone book. So we're already starting to sort of reuse ideas from back there in week 0. Well, what more can we do here? Well, let me propose that with binary search trees, we now have the ability to not only gain back binary search, but to trip over ourselves again by introducing a new problem. Like, it seems straightforward that my binary search tree as of a moment ago was beautifully balanced. Like, this is a nice logarithmic data structure, and in fact, therein lies the halving. Because you are splitting each node into two children, that's like pulling up these nodes much closer to the root than they would be if it was just a long stringy array or a long stringy linked list. The height of this tree, in other words, is log base 2 of n, where n is the total number of nodes in the structure. But I had to go to great lengths in making this slide, but also in code. If we were to write the code, we'd actually have to jump through some hoops to make sure that when we insert numbers into this structure and when we delete numbers from this structure, that everything stays nicely balanced in this way. But let's consider a sort of a perverse corner case whereby the numbers you insert, one after the other, just happen to be in unlucky ordering. For instance, suppose I insert the number 2 first. Okay, easy, it's the root of the tree. Suppose then I insert the number 1. That's easy, it gets to the left. Then I insert the number 3, I'm getting really, really lucky. So far, so good. That would lead to a very balanced tree of height log n, because everything's nicely balanced. But what if it's not that simple, and indeed we have this perverse case whereby I insert the number 1, okay, no big deal, it becomes the root. Okay, I insert the number 2, okay, no big deal, I don't have a third node yet, but that's not problematic.
Oh shit.
What if the next number I insert
Really?
is a 3? Well, if I want to maintain the
I'm currently on my S22 because I already updated from my last phone. I think you just saw my video, my Note 20 review. Yeah, I don't use that though anymore because the battery is broken. I currently have the S22 as well, but I haven't really updated the software at all because I know it's gonna, Samsung's gonna fucked up again.
And so the catch with binary search trees is that even though if they are nicely and beautifully balanced, do allow you to do binary search and achieve log base n log base 2 of n running time, you have to put in some effort to ensure that it actually does in fact stay balanced. So in the worst case, inserting into a binary search tree could actually be linear because it just gets long and long and long and stringy with just one perverse branch, unless you're smart about it. And in fact, with that previous picture, you know, there's clearly a solution here. Like, what would you do if this is what your tree was devolving into? You know, I'd kind of get in there and like kind of like rotate it around there so that 2 becomes the new root, and then 1's a left child, 3 is a right child. But you can kind of imagine from before break, like, oh, now someone's got to implement that code, and people have. And that's actually a discussion for higher level algorithms classes, how you can maintain balanced trees. But it does involve some cleverness with the pointers and updating things and essentially rotating the tree around if it starts to get too long and stringy. And so in general, with binary search trees, if you do make that optimization and you maintain balance, it does not devolve ultimately into big O of n. You can ensure that it stays in log of n for not only searching, but insertion and deletion as well. So long as you don't just blindly stick it in, but you kind of rejigger things as needed to keep things nicely balanced. Okay. So another data structure.
Yeah, I'm the notification for the software update has been very like in your face, but I haven't really updated it. So thank you for the heads up. I'm not updating the One UI.
Dictionary, and a dictionary is actually something with which we're all familiar with in the human world, whether it's in English or any other human language that associates words with definitions. You can kind of think of a dictionary as being like this 2-column chart whereby you've got a word on the left and its definition on the right. Word, definition, word, definition. Turns out that this is actually a wonderfully useful data structure to have access to beyond lists, beyond arrays, beyond trees even. The ability in code to associate words with definitions, or more generally, what we'll call keys and values, is just super useful. Why? You can implement a phone book as what really is a dictionary. Instead of thinking of it as a word and a definition, think of it as a name and a number. And throughout the world, there's just such a common need for associating something with something else. A dictionary lets you do that, associate keys with values. The keys are very often strings, like someone's name, for instance, or a word. The values are very often also strings, or maybe numbers, phone numbers, or the like, or even structures, like persons that have not just names and numbers, but email addresses and student IDs and bunches of other information as well. In fact, in a few weeks' time, when we focus on databases, we'll return to this paradigm of having keys and values to get at interesting data that we care about. Well, where do you see these? Well, phone books, whether it's physical or virtual. In a phone book, of course, we've got like names, ideally alphabetized by first name or last name, and then the value.
Still not entirely sure why we couldn't access the site.
Sort of everywhere, even though you might not in the real world think of them as such.
Oh, now I can access the site?
As a dictionary.
Okay.
Sort of like these 2 columns, name,
never mind.
A number. The catch, though, or rather the appeal of a dictionary, really, is that you ideally want it to be super fast. And that was the goal of the phone book, too. I could either do the linear search, 1 page at a time. I could do slightly more intelligently, 2 pages at a time, plus an extra step to double back if need be. But log n, as of week 0, was like as good as it got when actually searching for information. But what if I told you that there's maybe a way to implement this idea of a dictionary, otherwise known as an abstract data type that just has keys and values, but I could implement it with a data structure, an actual data structure that maybe actually gives me constant time. Like, that's sort of the holy grail of algorithms and data structures. Can you build it so cleverly that there's no dependency on n? You can just get at data super, super fast, constant time. Maybe not one step, maybe 2 or 3, but super, super fast. And that's in fact where we'll focus for the remainder of today. Can we find this holy grail of a data structure and algorithm that gives us constant time access? And all we have to play with is time and space and maybe pointers and memory. I think we have all of the building blocks thus far. So how might we set out on this particular goal to achieve that? Well, let me give us one new building block or ingredient, which is this notion of hashing. So hashing relates to what's known as a hash function. And a hash function, like any function, takes input and produces output. And the idea of a hash function ultimately is that it allows you to decide where some value goes in memory. So for instance, here are, by design, 4 buckets on stage for the 4 suits of a deck of playing cards, for instance. So we have the spades, the hearts, the clubs, and the diamonds here. And if you had a deck of cards, like 52 cards here, we've got the jumbo version online, how might you go about like sorting these in order from like 2, 3, 4 on up to Jack, Queen, King with the ace either at the top or the bottom, depending on what you prefer? How could you go about sorting these? Well, you could kind of just like, spread them all out and start making a mess of things and figure it out, and it takes some number of steps to get through all the cards. But a lot of us, myself included, would probably bucketize the values just to make a big problem the same as like 4 smaller problems. Like give me all the hearts, all the diamonds, and the other 2 suits in separate piles. And buckets is actually a term of art in computing. To bucketize something means to put an input into a location. So what do I mean by this? Well, here we have the 4 of clubs, so we'll put this in here, the queen of clubs in here, 8 of spades here. And as I do this, of course, I'm sort of making the problem smaller and smaller so that at the end of the day, it's going to be easier to sort like 13 of these cards instead of all 52. So here we have the 6 of diamonds. We have a bug, so like the program would crash if you don't actually have a bucket for it. So that's sort of an exception. Here we have another 2 and a 10. And even though this is still going to take me 52 steps, I bet you if you timed me, I could sort 4 buckets of 13 faster than I could sort 1 bucket of 52. And that's sort of the general idea. Bucketization helps sort of take an infinite or a very large domain and map it to a smaller range of values. So from 52 possible inputs, or 53, into 4 possible range values. So that's actually a building block, an idea that we can use. And hash functions are simply math or code that does exactly that. Takes as input some value and spits out as output some other value. But the key is that you go from a large or an infinite domain, any possible number of inputs, to a very well-defined finite range of values. 4 in this case, for instance. And it turns out that if you're on board with this idea,
I am from Indonesia. Where are you from?
Input this and produces output that, we can actually build something that are called hash tables using that. And a hash table, as we're about to see, is essentially like the offspring of a array and linked list together. It's somehow a combination of the 2. So for discussion's sake, I'm actually going to draw an array vertically, which we don't normally do, but who really cares? These are just artist renditions anyway. So here's an array with 26 buckets, for instance. And suppose that I'm implementing a hash table that I want to ultimately store names of people, for instance, so that I can implement a dictionary, key value pairs.
Well, isn't it like, what time is it in India? Isn't it like midnight, or is it like 2 or 3 a.m.?
The phone book is a specific example thereof, but a hash table is one way to implement a dictionary. Another way to implement a dictionary would just be a really long array, and you just put all the names and numbers in one long array. Or you use a linked list, and you put all the names and numbers in one long list. The downside of those, of course, is that maybe it's big O of n, maybe it's big O of log n, maybe it's big O of n, but I'm talking about constant time now. I'm trying to take a step toward a data structure that maybe somehow leverages the best of both worlds, arrays and linked lists, and gets me closer to constant time.
Constant time. Okay, so
using hashing
we're using, okay.
So here are 26 buckets drawn vertically, and let me propose that this location 0 represents the letter
2 a.m. man, can sleep.
Represents the letter Z. So depending on someone's name, they're going to end up over here, or somewhere in between. I think that's not all that new, but it's an incarnation of bucketization. Instead of 4 buckets, I've got 26 buckets, and I'm going to use a person's name as input, specifically the first letter of their name as input. So how might this work? Well, here I've numbered them for the sake of discussion. Now let's more concretely use their ASCII letters that correspond, A through Z. And suppose now that, once you're on board with that model, I want to insert someone like Mario into this. Well, I think I'm going to put this at location 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Even though it's the 13th letter, it's 0 index, so Mario with an M ends up in this bucket here, so to speak. More specifically, in the array location. Everything else for the moment.
Have you go to doctor for that, or is it like
L comes before M, so Luigi goes in this location 11 here.
no medication? No, is it like what's like the cause of it?
Instead. So this actually seems like a great system so far. We've got Mario, Luigi, Peach, and maybe all the other Nintendo characters in here ultimately. How many steps does it take to look someone up? It's already constant time, right? Because if you give me Mario, I just know, okay, M, I can do the ASCII value trick that we did weeks ago. That's 12. Boom. I can jump in an array with constant time to
Just in my chest shoulder.
You give me
Well, I
little
mean,
strings
if
like
you just
URL,
you went to the gym, you
P,
should
each P, got it.
be tired, no?
Nothing.
You're not
So
tired?
already I seem to have a system because I'm hashing on not the suit of a card,
Oh,
but the
every
fact
time
that
I
I
went
want
to
a
the
name
gym or like
in
I
a
work out
structure.
at the
I
at
can rename
night,
that
like
name, presumably
at
with
10 or like
URL.
at 11, I'm already like
This is gonna mess up
sleepy.
quickly, especially if you're a Nintendo fan. What could go wrong with this model with 26 buckets like this? Yeah. Yeah, I mean, what's going to happen as soon as I have two characters whose names start with the same letter in the Nintendo universe? This is eventually surely going to happen. So far, I've gotten lucky with all of these other characters, but I do think, indeed, before long, I'm going to have what we're going to call collisions, whereby here, two L names somehow collide, and I need to deal with this in some way. Now, one way to deal with a collision in this sense was, okay, I want to put it here. Okay, Mario's space is taken up. I can put it where the N names would end up going, but that's a little stupid because now I'm just going to make a mess of things eventually if I just resort to randomness or first available spot, and I'm definitely not going to get constant time. That's going to quickly devolve into linear time because it might be all the way down here if that was the first available spot. But what I could do, if I keep going, linked lists,
Ah,
so that
okay.
means, no pun
Got it,
intended,
got it.
I could kind of link all of the similarly named names together using a linked list here. And so this is why I say hash table is like an array of linked lists, because here's the array. It's kind of like your quick cheat sheet, your buckets for getting into some of the data quickly. But then if you do have collisions, okay, let's deal with it by just having a linked list that can dynamically grow and even shrink as you add or delete people. From this address book here. Why a linked list? Well, I could use an array. I could use a massive two-dimensional array, but in your mind's eye, you can just imagine how much space you're wasting if you're pre-allocating 26 times 26 locations here, or something like that, just to have enough room from the get-go for these names. And let me go ahead and add a whole bunch of others from the Nintendo universe. Collisions are actually going to happen pretty commonly, and there's actually this principle in statistics known as the birthday problem, whereby if we surveyed everyone's birthday in this room, essentially with a small number of people in the room, we would have a very high probability of collisions. And so
After this, I think the lecture is in, as soon as about finishing like 20 minutes. I think the next one is I'm gonna try to look at the practice question, and if I can't solve it, I'll do it. If I couldn't solve it, I need to do a website update. So I'm manage this website for an upcoming video production house. And yeah, they had a new project recently, and I kind of want to update the list of the projects here. So yeah, that's what I wanted to do, like update the new site and kind of refactor some of the background. And yeah, basically that's what I want to do after this.
So here too, even if
Because it's
you
only been
recognize
what,
some of
like
these names,
half an
pretty
hour.
quickly do you end
Yeah.
up having collisions in a world where you're just looking at, for instance, the first letter in someone's name.
Diddy
So
Kong.
this is not a
Oh,
great outcome. Why?
what?
Because imagine the perverse
Oh, it's
case.
like the
Suppose
yeah.
that we get really unlucky and every darn name in this world starts with L. Well, it doesn't matter that you have this array, and it doesn't matter that you're calling it a hash table. At the end of the day, this algorithm for a hash table could still reduce to big O of n, because in the most perverse case, all n names are in the same bucket and the linked list at that location. So who really cares that you're calling it a hash table? You're not using 25, for instance, of the locations. But that's sort of a theoretical risk. Is that really going to happen in practice? Now, definitely with Nintendo, there's a lot of collisions here, but that's because my hash function is actually pretty naive. I chose a fairly simplistic hash function, but maybe I could be a little more clever about that. And in code, I could take into account more than just the first letter. So for instance, if I want to get closer to this holy grail of constant time access, let's just think a little harder and implement this data structure a little more intelligently. Well, first and foremost, it doesn't take that much effort to implement the code for this. Here again, as we've seen for a couple of weeks now, is how you might implement a structure for a person. Well, how might we go about implementing a hash table using typedef and struct and pointers, as we've now seen? Well, I would propose that we could implement a node for people as having a name and a number, just like always, but also a pointer to the next one. So in the picture you saw earlier where we had Mario and Luigi and Peach, each of them was this rectangle as I drew it. You can think of each of those rectangles as a person structure, but in addition to having a name and somewhere in there a number, there was also a little bit of space left over for the next pointer to someone else whose name starts with the same letter. So implementing this in code is actually not all that hard. And in fact, if you want to have a hash table of size 26, no big deal. Just say you want a table, or whatever you want to call this thing, of 26 node pointers. In other words, that vertical that I drew had 26 locations. Each of those was initially null, I proposed, because the hash table was empty, but it was really a list, it was an array of 26 pointers, because each of those could be the pointer to the beginning of a linked list. So this is how you can implement a hash table in code. Sort of one line, at least at a glance. You still need all of the functions to insert and delete and so forth, but this would really just be a hash table.
Okay, never mind. I'm gonna practice the pointers.
But what if we get a little smarter indeed about...
I'm 19, 5'7", 60. What weight should I reach to look muscular? I have 50%. Dude, this attack and programming channel. I haven't decided to make gym content yet because I'm still in the process as well. You know, once I get the proper gains, I probably will make a gym content. But as of right now, no. Like no, it's not there yet. It's in progress, but it's not there yet. Like it's there, but it's not there yet. You know, I'm self-aware. But you're 19. You're 5'7". You're 60 kilo. Wait, I forgot the 5'7", 2 centimeter. Sorry, I prefer centimeter. Sorry, 5.7. You are 170 and 60 kilogram. I think your body weight to your height is pretty ideal, because if I'm not mistaken, it's like the wait, yeah. I think you're pretty on track to be ideal, you know. See, you're in between, in the middle. So I think your weight and height is in a pretty good spot. Are you currently on a bulk or currently on a cut? Are you currently like just maintenance? Just wanna get some, probably, what do you call it, like body recomp? Body recomp? Are you currently just want to build muscle, or like what's your current goal? And of course your diet and your routine, like how is it, you know? Like I can't just really know based on just height and weight itself, you know, because it's, yeah, a lot of factors, right?
The hash function. So here's how we describe problem solving all this time. A hash function is just sort of the algorithm in the middle in this story. So if we input Mario as input, the output should be 12. If we input Luigi as input, the output should be 11, and so forth. But if that's the problem, we keep returning 12 and 11 and other such numbers a lot, well, let's not look at the first letter alone. Why don't we look at the first two, the first three letters? And I bet, probabilistically, we can drive down the probability of these collisions, because there's not that many people whose names in the Nintendo universe start with L-A-K or L-I-N or L-U-I. That really lowers the probability of collisions by increasing, in this way, the number of buckets.
And to get physique like Moist Critical. I mean, he has like slipper build, like his hands are huge.
I could actually increase it to 17,000 plus if I do it in this way, looking at the first three letters. That would seem to really help. It doesn't make the code all that more complicated. Here, for instance, is how you might implement in C a pretty simple, if naive, hash function. Given a word, aka a string, you want to return an integer, like 0 or 1 or 2 or 11 or 12 or so forth. So we've seen toUpper before in the C-type library. Just look at the first letter in word, convert it to uppercase just so the math is simple, subtract capital A, which we know is already 65.
65, yeah. If I remember the ASCII.
To 25. So you can imagine in your mind, we won't do it on the screen, but you can imagine just maybe looking at word 0 and word 1 and word 2.
Are you tracking your calories as well? Are you tracking your calories or your macros, or just like, you know, not there yet? Because I really like this site, even though it's you are 19, male, and that. How many exercise do you do per week? 1 to 3 or 4 to 5 times?
Doing some similar math and returning a number between 0 and roughly 17,000 instead, to get back a much larger hash table instead. What's the downside there? Because I'm proposing that the code's not that hard. It's like a couple extra lines. What's the downside of having a bigger hash
Okay,
table?
so you definitely wanna at least like increase your weight, right? Like, or maybe do recomp. How much do you like exercise per week? 6 days. 6 days, bro. Okay. That's good, but have some rest, right? Still have some rest, okay? I guess 6 days is fine. Just at least you have 1 day for rest. Let's see. Okay. Very active. Oh my god. Okay. Since you're very active, you need around 2,700 in terms of calories, and I don't know how much the percentage for protein or like how much protein? Hello, Alfie. Welcome. So for Mookie, push-pull leg. Okay, so you do like 2 day. Okay, yeah, it's pretty good. For the past like years, I haven't been in the gym for almost a year. I've been doing it at home. But before I stopped, I was doing full body because I can only do like 2 days per week because stuff and exams and stuff. But I was doing full body. I do eat rice sometimes. Ja, wir essen auch Brot und manchmal
Just enough space to have
Reis.
collisions, but
Sometimes Reis, but
a little louder. Yeah.
ja,
If
ich
you're losing more
habe
space up front.
fast jeden Tag Brot essen. Yeah, I eat bread for breakfast almost every day. Almost, not every day, but almost. So very German.
In fact, the dots on the screen were really because I didn't want to draw a microscopic array with 17,000 locations, which most of which are not actually going to get used. You start wasting space at that point, and it becomes a little silly because in the world of Nintendo, it's probably a pretty sparse universe, so to speak, whereby you don't have any names, to my knowledge, that start with AAA, let alone AAB or AAC or BBB. I mean, there's thousands of permutations that just are not going to be useful. So that maybe isn't the best solution instead. As an aside, you can also specify that these inputs are constant because as an optimization, you know that the words coming in are not going to change. And as an aside, let me propose that with an actual hash function, if you know the array is 0 indexed, you don't need to even return an int. You might as well return an unsigned value so that it's 0 on up, no negative sign, which would be an optimization here. But that still doesn't change the fundamental reality that adding more complexity beyond this is going to certainly increase, it would seem, the amount of memory that we actually use. So maybe the fundamental problem is that just looking naively at the first letter in someone's name is maybe not the best solution anyway. And in fact, at the risk of disappointing, the whole hash table, even when we use 3 letters of a person's name, technically speaking, theoretically speaking, it is still big O of n. Because even though it's unlikely, you could imagine a perverse scenario where all of the names you insert somehow start with the same first 3 letters. There's no guarantee in this model that you're going to avoid that. What then is the appeal of a hash table to begin with? Well, if you've got 26 buckets, or heck, 17,000 buckets, let's call it k as a constant, well, really, if we get into the weeds, if you have a uniform distribution of inputs, that is to say, if you have a bunch of random names that
Not gonna lie, this second half of the lecture started the professor started to use some high level vocabulary that I need to like, okay, he meant this, like, oh my god, like soon after the break, the comparison between like even though like the linked list was like almost like half of the video, but after the break and starting with the trees, his vocabulary is definitely way higher compared even to the previous week's stream. And oh my god, this is insane. I'm still, yeah, I don't think I'm gonna try to do the practice. I'm gonna do the pointer practice from like one of the site because oh my god, this is I'm trying to like, yeah. I started going to the gym 7 months ago. I tried to get 150. Oh, that is nice. That is good. What do you eat, man? What do you eat every single day? Do you know if you never see you bought one sack of rice, you might get viral? Why? Really? Well, I mean, the thing is, I don't use car here, and I only use like the public transport. Of course, if I bring like 20-kilo bags of rice, if I bring 20 bags inside of the tram or in the bus, yes, of course, the people and the neighbor will look. But so far, I've only been buying the 1 kilo because I don't eat rice every single day. I sometimes switch my carbohydrates between like rice, bread, sometimes pasta, and sometimes like wrap, like those like tortilla wrap, or sometimes even flatbread. So I try to diversify my carbohydrates. But for the protein, it's definitely the easiest and cheapest is mostly just chicken and eggs, sometimes sausage. And yeah, recently I finally find out like a halal butcher and a halal like supermarket which sells like the halal meats and sausages. So yeah, I've been shopping there. Holy 9 eggs in a day. Holy, okay.
Technically, those linked lists that I described.
Yeah, he's talking about hashing, but on C still.
By k, because if you've got k buckets, again, whether it's 4 or 26 or 17,000, on average, hopefully, each of those linked lists, aka chains, is going to be n divided by k. Now, we know from our discussion of big O in the past that like if you have a constant value, like a number or a lower order term, like who cares? That's still really big O of n. But here is now in week 5 where we see kind of a dichotomy between the theoretical running time of an algorithm and the actual wall clock time of an algorithm. Like the reality is, if you take the size of your data and divide it by 26, let alone 17,000, it is going to be way faster if you look at the clock on the wall or the time on your wrist than it would be if it were actually running in n steps alone. So yes, hash tables technically are in n divided by k, which is really just big O of n. But in practice, if you are smart and if you are clever about the hash function you use, and ideally use something that's more clever than just looking at the first letter, you can probably create, in the best case, an ideal hash function that somehow, magically, it would seem, ensures that you never have collisions. Because if you can find that ideal hash function, or at least a really good hash function, the probability of collisions is probably going to be so low that even if occasionally the thing devolves into linear time, most of the time it's going to be indeed constant time, aka big O of 1. So in short, hash tables, not really constant time, but with a good hash function, they can be pretty darn close to constant time. But there's one final data structure we thought we'd introduce today, this one pictorially for the most part, and that's known as a trie, which is somehow short for retrieval, even though that's somewhat differently. But trie just means it's a data structure for retrieving data. It is an alternative data structure via which, again, we can implement dictionaries,
This is
value pairs.
the first time I ever heard about it. Trace?
Dictionary with an array, a linked list, now a hash table, now a trie as well. But we get different running times based on those various structures. So a trie is a tree of arrays. You can think of it as. So really all we're doing now is just kind of mashing together things we've already talked about and seeing what kind of weird Frankenstein data structure we come up with. But in this case, it's actually going to give us, I think, true constant time, but with a downside. So here's the beginning of a trie. And a trie is indeed a tree of arrays. And each of those arrays represents a letter of the alphabet, typically, A through Z. So let me stipulate there's 26 boxes here written horizontally because I just wanted to fit on the screen more like a typical array. And the way you use the arrays in a trie is to have an array of pointers. And if the person's name starts with A, you sort of use one of those pointers to point at another node, which is just another array, for the second letter. And then a third array for the third letter, a fourth array for the fourth letter. And essentially, you use arrays for each of the letters in your input strings. So what do I mean by that? Well, here might be that array of size 26, A through Z. Suppose that we want to insert like Toadette into this data structure initially, or maybe shorter, Toad, for instance, one of the characters from Nintendo. So here is T's location here, and I've just highlighted it because if I have a word that starts with T, I'm going to actually change this null value to be a pointer to another array. And that second array shall be used to represent the second letter in this person's name, like O, and that letter is going to map to another array, whereby this location, A in Toad, points to finally a fourth array, whereby now at the D location, we have some kind of sentinel value, some kind of variable that says X marks the spot, a name ends here. So there's a way to do that in memory. But we're using 4 arrays, one for each letter, to map out the person's name. But we can go further. Suppose that there's another character in this universe, like Toadette, which is a superstring of this string. So it's a longer version thereof. That's fine. We can just add a pointer from the D location to another array, then from that array's E location to another array, then from that T location to another array, and from that array's T location to a final array E. So in other words, each of these arrays is just an array of 26 pointers, or really 26 structures of some sort, and somehow in green we're just indicating that a name ends here, and with the E, a name ends here. And we can do this again. If we have Tom, for instance, as a third name, we don't need any of these arrays. We can actually encapsulate T-O-M in the first 3 of those arrays. Now suffice it to say, this is a lot of arrays, but what have we gained? Well, if you imagine this data structure getting crazy large with lots and lots of names and lots of arrays inside of it, it turns out that the amount of time required to look up someone's name or to insert someone's name has no dependency on how many names are already in the structure. Case in point, when I added Tom a moment ago, there was all of this bulk in the data structure already, but we didn't have to traverse any of that because we just go T-O-M, and we don't depend on how big the data structure already is. It does not depend on n. Technically, how much time does it take to insert or to delete, or to search for someone's name in this? It would seem to depend only on the length of the person's name. So T-O-A-D-E-T-T-E. So I think that is 8 steps total for finding Toadette. 4 steps total for finding Toad. 3 steps total for finding Tom. Those are really small numbers. And if you imagine, there's surely some upper bound on how many characters are in the longest name in the world. I don't know if it's like 10 or 20 or 50 or whatever, but it is finite. It has nothing to do with the total number of words in this tree. And so the implication then is that the amount of time it takes to search for, to insert, to delete a name in a trie is by definition constant time, big O of 1. Maybe it's big O of 2, maybe it's big O of 50, but it's not dependent on n. Because as massive as this structure gets, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, that's all the steps it takes to find any of those names. It's dependent only on the length of the name itself, which has some kind of upper bound. So how might we implement this? This is probably the most common way. We just redefine a node in the world of tries to now be a structure like this that contains one in an array of 26 more pointers, each of which points to a node. And then we need some other value. I'm calling it char star number.
When I was 18, I was me too, man. When I was I think when I was like 18 to 19, I was only 56. Sorry, 57, 57, 58. End of high school, and then like COVID, and then like uni start, and then like right now I'm at 79. So yeah, I started to eat. I started going to the gym. At least like if I'm not going to the gym, working out at home, trying to eat more protein. Started to use some protein powder, for breakfast or sometimes for just any additional meal. But yeah, I totally understand your like history, because it's the same. I was also very, very skinny when I was in junior high school and even like high school.
Number, because I want this try to be storing people's names implicitly and numbers explicitly. So if I want to store something like +19494652750, like John Harvard's number, I'm just going to store it as a string inside of the same structure. So a moment ago when I had the little green dots, the green dots in
I am, what is 100 centimeter? 5'9". Oh, sorry, no, 5'11". 5'11".
This string is not null, it's someone's actual number, which means if you see a non-null number, well, there's Toad's number, there's Toadette's number, there's Tom's number instead. This is a sufficient data structure to implement that notion of a try. All we need, of course, is one pointer to the root of the whole darn thing. And so ultimately, like, we found our holy grail. Like, tries are by definition constant time, because no matter how big the data structure gets, there's no dependency on how many elements are already inside of it. It has no effect on the running time per se. But it must come at a cost. What's the trade-off then for a try?
It uses so much memory.
Space? What space? Yeah, the space to store all of those arrays. This is like the logical extension of not using 3 letters of a person's name, but every letter of a person's name. And the math there just means a massive amount of memory, because you need an array for every possible letter of the alphabet, would seem, even if most of those letters are not actually used, because there's just no name that needs those particular letters. So by significantly using more memory or space, you can significantly decrease time. And so that too is potentially a trade-off you may or may not want to make. So today was ultimately about introducing a bit more complexity, the last of our complexity in C, and these building blocks of pointers and memory to sort of stitch these things together. And I'll stipulate ultimately that the kinds of data structures we've talked about today, whether it's queues and stacks at the beginning, or linked lists in some form, or dictionaries, key value pairs, phone books, and the like, they're sort of everywhere. And even hash tables you can find in like Harvard Square or in New Haven as well. For instance, this is a photograph from this morning of a certain takeaway restaurant with which some of you might be familiar. Anyone know what place we're looking at? Sweetgreen. So Sweetgreen, a little salad shop in Harvard Square. What are you looking at? Like, this is a photograph of the shelves they use to distribute salads when you order them in advance online. But what really is this? Like, all your friends will be very impressed that you now see
hashtag. Yeah, it's a hashtag.
That's
right.
This is effectively a hash table. Why? Because when someone has a salad with their name on it that came out of the computer, they're going to put it in a specific location. This is location A through E, this is F through J, K through N, O through Z. And so they're hashing it to one of these 4 locations, not unlike one of these 4 buckets. Of course, here, they're not using really an array of linked lists that can grow endlessly. This is actually sort of like an array of arrays, because I can only imagine storing like so many salads on this shelf. And just imagine, I'm sure this happens during the busiest times if you go in at like 12:30 p.m. and lots of online orders have come in. If they run out of space, for instance, in the A through E section, where do they probably put the next salad? Even if that person's name starts with A through E, maybe over here, maybe over here. Like to my point earlier, you can kind of just plop things anywhere. And so the real world, like this data structure might indeed devolve. But I do dare say after today, you'll start to see hash tables and trees and tries and all of these structures in different places. And hopefully what we've given you now in a CS class is sort of a mental model for the upsides and downsides of these structures, but also the technical skills with which you too can build them virtually as well. That's it for today, and we'll see you for Python next.
Amazing, bro. I love Professor Milan. This is amazing. Okay. I'm definitely not gonna be able to do or perform any of these the stuff. Sorry. The yeah, definitely not yet, because man, I really need to kind of really want to deepen my knowledge regarding the pointers. So I think we can try to implement this. At least like try to do that. So what is this called again? This is binary search. So pst.c. Yeah, also I just wanna like patch type a little bit, you know. Okay, I forgot what's the okay, cool. Like on the video? Which video? Okay, let's play some you know what, it's fine. Let's just make it like this. You guys could just hear me type or whatever. Okay, what is this free tree and what is this print tree function? Oh, this is the recursion one, right? Okay. Print tree is just print tree root left print root. Okay, it's just okay. How does this work again? Wait. So it calls the okay. So it's okay. You know what? Let's okay. Let's try to run it and see how it goes first. Because not gonna lie, I don't follow how does this. It's just gonna be. Okay. And then the print tree as well. Okay. Okay, cool. Okay. Like on the video, the lecture, well, which one? Like, is this just an implementation of this, right? But like, if I didn't see this example, like I wouldn't really know how to do it. The lecture, like on the video. Oh, like the video? Yes, of course. There. Oh, that's cool. I like the animation. Cool. Okay. I know I can copy paste it, but I just really wanna touch type, okay? So apologies. Tree size 0. to list if n returns 0. Oh, okay, this is just adding the number. Okay, okay, this is the actual, okay, yeah, the actual implementation of the trees. Number to list. So we add just 1, 2. When did we add the root? Okay. 3 and add number to list. So if you run it, what will it show? Man, I feel so confused. Okay, so it created another number as a place. Okay, small elements on the left side, larger elements on the right side. Ah, oh yeah, yeah. Okay, okay, yeah, I remember. So since this is the number 2 is going to be on the left. Okay. Number 2 is on the left, but this is set to null. So, sorry. No. Okay. So, okay. Okay. 4 is the root. No, 2 will be the left because smaller than 4. If your goal want to be survival, I think you don't need much pointer, bro, unless you like meta. Yeah, okay. It's just that this topic really itches my brain in the sense that why are you so complicated sometimes and the other times doesn't? But I don't know. Should we? Okay, wait. I think if I remember correctly, I set up some. To be honest, yeah, I don't really care. The thing is, I just wanted to understand why and if it's necessary, and like if I just accept. This is done. Make work with Astro, continue for code cam, roadmap, SSH. I think it's pretty good. It's just a. I think let's go to the JavaScript DSA, I guess. Like, can just go straight. I think your goal is better to study with my zero to Russian instead of running topic. Yeah. The thing is, right now, I think what I want to do this is I'm really torn between like, okay, should I really get down to the basics of basics and fundamentals again with like the CSS, HTML, CSS, JavaScript? Because even though I'm really wanting and focusing more on the front end side, but yeah, your argument is true. I don't really need to go in that much depth into the pointer. So I guess the next one we could just focus on what is it that I want, and that is JavaScript. But at the same time, the learning of the essay is more on the for interview part, because even though the role I want is probably front end and don't really require much essay still, but I guess it's just gonna help to train and make my brain think again. So I think we can go into the JavaScript ESA after this because we already know most of the basics of the difference of the different of algorithm and data structures. But now, since we're focusing more on front end with JavaScript, I think it would be proper to continue with the JavaScript. And I think we should continue with this. I've already like watched and seen a little. Yeah.
My name is Vishwas and welcome to a brand new tutorial series on algorithms with JavaScript. In this introductory video, we will briefly go over what this course is.
I think I already watched like a couple, but okay, I'm gonna. Yeah, there we go. It has like 35 lessons. I already watched until.
Vishwas and welcome to a brand new tutorial series on algorithms with JavaScript. In this introductory, for our first algorithm, we're going to learn about the Fibonacci sequence. Here is the problem statement. Given a number n, find the first n elements of the Fibonacci sequence. But what exactly is the Fibonacci sequence? In mathematics, the Fibonacci sequence is a sequence in which each number is the sum of the two preceding ones. The first two numbers in the sequence are 0 and 1. For example, Fibonacci of 2 is 0, 1. Fibonacci of 3 is 0, 1, and 1. This is because the third number is the sum of the previous two numbers. Similarly, Fibonacci of 7 is 0, 1, 1, 2, 3, 5, 8. You can pause the video for a minute to verify that each number is the sum of the previous two numbers. Of course, the first two numbers are 0 and 1, as I had already mentioned. Now, if you've understood the problem statement, please pause the video and try to solve the problem. It is completely fine if you're.
Oh, really? Still? Oh, okay. Wait. Is it expired already? Wait. Yeah. Let me try to change it. Damn, sorry. Okay, let me try to fix that. Sorry, I haven't been opening Discord because I was at work. Understanding and using. Oh my God, seriously? You can check syllabus to progress essay. By the way, it's really long way. Oh my God. Okay, wait 1 second. I'll go make another invite link. Mm, copy link. Okay, let me change the description. Which one is the permanent one, man? I don't know. Okay, expire after never. Yeah. Okay, it's not. Okay, which one? How do you do it? Man, such a. Okay, settings. Invites. Okay, that's not working. Copy. Let me share. Yeah, okay, please do. Even though I don't know if it's possible or not. Okay, can you please copy paste it in one of the chat and I will like put it in the link. Thank you so much. Linux distro religion. Holy. Oh yeah, it's the Pop OS. Oh shit. Okay. Stream alert. Okay. Wait. Only mods can do. Okay, wait. Oh my god, we have 778. Awesome. Wait, yeah. Let me try 1 second. Okay, wait 1 second. Okay, it's in here, and then there's invite, and then there's copy link, and then oh, edit invite link. I'm gonna choose never. Okay. Okay, wait. Let's do welcome. Welcome is like the invite channel, right? Yes, okay. Invite, and then we can do edit, and then we can do never, and then we can save, and then we can copy link, and okay, I'll update the link after this. So please go check the description. Live apply. So this is my latest. Okay, I couldn't really. Only mods can share the link on YouTube. Yeah, okay. I hate Windows 11 so much. Yeah, me too. I hate it too. Okay, how do I copy the file? Okay, wait. Like there, maybe. Okay. 1 second. I forgot the Astro NVM Uh, oh, holy, what is this? Cool. Okay. Let me update the description link if you wanted to check it out. Okay, you can try again if you want.
As failing to solve problems in this course will teach you a lot more than you expect. Alright, let's solve the problem together.
I've already done this
Head over
before.
to replit.com and create a Node.js template. You should see an index.js file where we can write our code. Let's begin by defining the function signature. Function Fibonacci parentheses curly braces. The function will have one parameter, n, which denotes how many numbers in the sequence we have to display. For example, calling the function with n equal to 2, 3, and 7 should return an array of Fibonacci sequence with the same length. Now what do we know about the sequence? We know that the first two numbers are 0 and 1. Let's create a constant called fib and initialize with an array of two numbers.
I installed like the Astro and Vim on like the Windows. I think at the time I was like testing it and I kind of really like it, but I don't know how to like update them. Uh, and I really forgot how to do like the setup and like the key binding to open like the thing, and it is just terrible. Okay, mappings. Next step is that, okay, how do I open the, it's not buffers, it's not commenting, completion. Oh my god, are you serious? It's space E, bro. Oh my god, yeah, okay. What was this about? What is it? Do I have a, yeah, okay. Sorry, back to this.
0 and 1. Next, we need to populate the remaining elements from the third element till n while satisfying the condition that every number should be the sum of the previous two numbers. To populate the remaining elements, we use a for loop that starts at index is equal to 2. Since we already have elements with index is equal to 0 and index equals 1, and we iterate till we have n elements in the array. So, for let I is equal to 2, I less than n, I plus plus, and in each iteration, we populate the value at index I, so fib of I, by adding the previous two numbers. So fib of I minus 1 plus fib of I minus 2. So if n is equal to 3, fib of 3 would be fib of 2 plus fib of 1. Fib of 2 in turn would be fib of 1 plus fib of 0. And we already know what those values are. This for loop populates the array with the required sequence. Once the for loop exits, we return the array. So return fib. And that pretty much is our implementation of the Fibonacci sequence in JavaScript. Let's Let's verify by running the code. We see the 3 arrays corresponding to each function call. Our code works as expected. What I would like you to do is take a pen and paper, trace the function execution for n is equal to 5. Write down what the value of fib array is in each iteration, and that will give you a much better picture. Alright, next it's time to determine the big O of our Fibonacci function. Pause for a minute and determine the big O. You can either determine how many times each step is executed and then approximate big O like we've learned before, or you can use sort of the thumb rule which accelerates the process. Here is a cheat sheet which can be used as a guide. You shouldn't completely rely on this, but it does help most of the time. Pause now, or let's estimate the big O together in 2 seconds. Our function contains one for loop.
Thank you for joining. I hope to see you on the Discord and other places. Have a great rest, man.
Big O is linear time complexity. So big O is equal to O of n. As the value of n increases, the number of times line 4 executes also increases. Well, that completes our first algorithm in this course. Hopefully, you're able to get into the mindset of problem solving and what to expect from each video in this course. Let's take a look at our second math algorithm in the next video. Now that we've understood the math algorithms, in this section, let's focus on the search algorithms. This section is pretty small as our focus is only on two algorithms: linear search and binary search. With binary search though, we will have a look at the recursive solution as well. The approach remains the same as math algorithms. I'll start off by mentioning the problem statement. What is the ask from us? I will then request you to pause the video and try solve the problem. We will then implement the solution together. I highly recommend you code along with me rather than just watching the video. Finally, we will determine the big O time complexity of our solution. Alright, let's get started with linear search in the next video. In this video, let's take a look at the linear search algorithm. Here is the problem statement. Given an array of n elements and a target element t, find the index of t in the array. Return -1 if the target element is not found. Here are a few examples to help you understand better. If you have an array with 5 numbers, -5, 2, 10, 4, and 6, and target element t is equal to 10, our solution should return 2 since 10 is at index 2 in the array. With the same array and t is equal to 6, our solution should return 4 and with the same array but t is equal to 20, the solution should return -1 as 20 is not present in the array. If you've understood the problem statement, please pause the video and try to solve the problem. Alright, let's now solve the problem.
Okay, I'm gonna try, although I'm probably gonna fail miserably, but okay. So we have an array input n and another element of t. Find the index of t in the array. Return if target is not found. Should we put the case of not found first or later? Because my first instinct and like noob is just a for loop. And then we're going to loop the array. So we're going to have yes, and now okay, to be honest, I haven't really applied any remote, or if I'm in Indonesia or in here yet. Do you have any like suggestion on where I could find or the best possible one? This is such a okay. No, this is not gonna work, but I'll try. I'm not entirely sure if this is correct or not because it's definitely not correct. Though it's okay. It's definitely gonna be wrong, but I don't mind. I just like to see if my uh t equals to 10. Did the job just learn COBOL? Actually, I find like a no, like I saw a bank here that asked for like a COBOL job, but they asked like 5, 10 years of experience. So like, man, I don't think I got time for that. And yeah, but it is definitely interesting. I mean, if the job is the goal, probably I would try COBOL just for the heck of it, you know. But we'll see how it goes. Okay, that yeah, I know it's not gonna work, but why is it undefined? Yeah. Oh shit, I forgot. It's supposed to be array. Sorry. Never mind. Okay. What is? No, no, no. Let's just use. Sorry. Let's do n for this, and let's just make this t. Yeah. This. Sorry. This is. Oh my god. This is such a terror. Okay. Sorry. This is I, and we're gonna return n. Sorry. No. Is this? Wait. You know what? Okay. We have a function that takes the array element of that, the n input, which is in this case array. Okay. So we're gonna loop through that array, right? For we have start with index 0 and the n. Sorry. No, this is not n, but it is length. Fuck, I forgot the function. Sorry. No. This is not. This is wrong. This is wrong. This is wrong. Wait. It is this. Okay. Let our length is equals to n dot length. How do you use it? Is it array dot length? Yes. Equals to, sorry, this is n dot length. And then we have find n. This is change it to r length. That's not right. Yes. And then if n is equal, if n0 is equal to t, it's gonna return I, or else it's gonna return -1. Yes, oh my god, you are correct. I forgot, you know, it's not C. So we use this. Or sorry, we use the 3 one so that it's exactly the same thing. Let's just use the 2 one. Okay, thank you, okay. Okay, that's not this is wrong. Okay. This should work. This should work, right? Because I don't know, man. Let's keep on trying. Okay, that works. That works, I think. Because okay, let's test. Let's just do 6 7. Because okay, if it's 6 7, it's not gonna work. It's gonna be -1. So it is correct. Okay, let's try -5. It's gonna be 0. Okay, that works. That works. Linear search. Okay. Let's do 6. It's 4. It's correct, right? Because it's 0, 1, 2, 3, 4. Yay! Is the t-value from index of the array? No, t-value is the target, the one that we want to search. This t here. It's the parameter. So I think
Together.
that works.
Before we write the code, let's understand how should we go about this in pseudo.
Ah, god. Oh, yeah, I should have done the pseudocode first. Yeah, that's why I forgot this.
As they come. In this algorithm, you start at the first element in the array and move towards the last. At each element, though, you check if the element is equal to the
Yeah. So, yeah. Okay.
If it is,
it works.
Return the index of that element. If you've gone through the entire array but did not find the element, return -1.
Yeah, okay, I really need to practice pseudocode. I understand the value of pseudocode now. I shouldn't just like raw dog like the one that I did, but it works hopefully.
If you've understood it with our signature, we have target equal to 10 significantly to go through E or so then traverse the
Okay, I could just do the r dot length here, the n dot length instead of doing this, so I shouldn't waste more memory to do this. So we can just do that. So we don't need to waste like memory for that. We can just do n dot length. And it would be the same. Yeah. Thank you. Okay, it should work. Yay. Okay. Nice. Yes. That's why I forgot. Yeah. Because that means I don't need to waste memory to hold that variable. Thank you.
Is equal to target return the index. So return I. However, if you have gone through the entire loop and did not find the element, return -1. That pretty much is the linear search algorithm. Let's verify by running the code. Format. We see the 3 values corresponding to each function call. Our code works as expected. What I would like you to do now is take a pen and paper, trace the function execution for this array, and target is equal to 10. That will give you a more clear understanding of the code we have written. Alright, Next, it's time to determine the big O of our linear search function.
It's gonna be
Pause
O
for a minute and determine the big O.
O of n, because the
Here is
amount
cheat
of
sheet which can be used as a guide.
loop is depending
Now,
on
our
how
results
long
estimate the big
the
O
input
to
of the
be.
array. Is that
Our
correct?
function contains one for loop. From our cheat sheet, we can say that big O is linear time complexity. As the size of the array increases, the number of times the if condition executes also increases.
Bro, we are on a RAM shortage right now. We can't afford to waste memories. Like, damn. Okay, I want to see how much NeoVim takes memory, because if it's taking more than Z, holy shit, that is insane. Okay. Okay. NeoVim is 80 mega. Okay, that is what I'm hoping and expecting. But of course, then again, I'm only opening like simple JavaScript files. So yeah, NeoVim still uses the least amount of memory compared. Okay, what is Edge on? Turn it off. I'm not. CentOS. Does running JavaScript even though not running the? Okay, how does Node.js work? What is it? Okay, cool.
That is about linear search. In the next video, let's take a look at binary search.
Okay, I'm gonna stop it right there, and I'm gonna end it because I'm quite tired already. Sorry to keeping it short, but yeah, DSA JavaScript. I'm gonna finish this hopefully tomorrow if I don't have any agenda, or if I could, if not tomorrow, then Monday or Tuesday. So yeah, I think we can finish this by all of this like super short, super concise. The explanation is very clear. I just need to really hone the pseudocode even better, I think. And after, let's make it here so we can do the JavaScript DSA in progress. And after that, I think I want to go back to HTML, CSS. I think I have been indulging in too much Tailwind CSS for this past couple of months. And I kind of want to or need to go back to our regular old root CSS. So I'm definitely going to do that as well in the upcoming weeks. And after that, CSS JavaScript, and then I actually wanted to learn Astro for making the blog, and I have two like quote unquote, it's not really a sprite, but like a backlog of websites that I need to revamp, and the other one is create new, and I really want to experiment and try with Astro because why not? Gotta add more stuff into my CV, even though I only did it like once. It's big O of n because runtime growth equal to input data, bro. If you have 1 million input data in JS, so that 1 million times 2. Okay, the input of the array, right? As because like it loops through the whole element of the array. Okay. Marvelous. Awesome. Okay. Yeah. So I think that's the upcoming for 2 weeks. And then I think we can do your suggestion with the roadmap.sh. But after that, but before that, I think I want to focus on the CSS. Like basic CSS, I really want to do, because I saw on Twitter a lot of like CSS new updates. Like they have like if statement in CSS. You can do like view transition. You can do all sort of kind of things. I kind of wanted to focus, or at least like I want to learn a little bit more about like the animation stuff where I can make like interactive UIs, because my goal is to be like the front end anyways. So yeah, I think you're right again, that you are absolutely right. But yeah, it's been nice, it's been good. I think going back to DSA really made me appreciate the low level language and all the all the amazing developers that built on top of those low-level languages and allow us to just hog and consume memory with JavaScript, Python, and all other high-level interpreted garbage collected language, you know, because who needs yeah, malloc and pointers and yeah, but I really it was really fun to go back to that. It kind of made me able to, oh yeah, think about more about memory, think about, okay, yeah, why data structures and algorithm exists, why is it like important, because it's, yeah, very nice, very cool. But yeah, we're staying on track on creating, basically making actual products. So I have a list of ideas of like projects that I like my idea dump, and I haven't really made all of them. And even like for Omwerk and all the other stuff that I want is, yeah, it is all the projects that I really wanted to do, that I list, that like, oh, I have this stupid idea, or like, oh, I had it in a dream, or like, I want to make it a site or something. But yeah, it's all in here. You guys could steal it. It's fine. I just really, yeah, I have like 29 ideas that I kind of really want to make, but yeah, it is what it is, I guess. So I guess in the next 3-6 months, once I get all the basics correct again, once I master HTML, CSS, JavaScript, I could try to make whatever it is that I want. So we'll see how that goes. Well, I mean, yeah, but we're on a RAM shortage for at least a few years until what's the company, until TSM, no, TSML, TSMC, until TSMC, or until like the AI bubble popped and like all GPUs and RAM prices go down. I think I'm gonna try to appreciate memory and making like good and efficient code as possible, you know, because I mean, like, look using Z for like 2 weeks now, like 3 weeks. It is such a nice experience compared to VS Code in terms of speed, especially when I stream. But of course, feature-wise, Z still lacks a lot. The AI, I love that. But oh my god, okay, I understand why having actual knowledge on software and all of this is very important. But yeah, I guess, yeah, I guess I really need to write down like why am I actually doing this instead of just looking for a job. Am I really wanting to looking for a job? Is it a job that I really want? Would I be satisfied by it? What? Okay, so it is what it is. Okay. Oh, I have some notes here from the previous line. Okay. So yeah, basically, oh, well, this was, yeah. I appreciate Tailwind because I couldn't even remember this original CSS for the grids. I still remember like using EM and REM. Like I'm rarely use Pixel anymore. Media queries. Oh my god, Tailwind classes. Okay, yeah, Tailwind classes, bro. Amazing. But I kind of want to learn like the CSS animation. A lot of like the uh pseudo classes on CSS that I didn't really had the chance to like focus on or work on. I don't know if that's important or not, but yeah. Yeah, Rust, by the way, of course. But yeah, okay, Alfie and anyone watching, thank you so much for hearing me yap tonight and burning my brain in algorithm and DSA and basically a bunch of ones and zeros. Like at this point, I'm just gonna learn Morse code, you know, or I don't know, expensive kitchen. But the busier you are, the less you cook, though. Oh, that I don't know, man. I really love seeing like or like going into expensive like kitchenware stuff because they are just so good, or like saw them on like YouTube and stuff. But yeah, it is what it is. Okay, I'll see you on some other time. Oh my god, why are you not? Okay. The busier you less you cook. Well, I mean, like cooking for leisure, you know. It is what it is. I know, I know. I stopped using Notion because it was like slow, but like right now it's like, oh, it's actually pretty fast. Again, I don't know the Notion team, what did the Notion team did, but okay, what is this? Welcome home. Whoa, okay, cool. Okay, yeah, that's it for today. I hope everyone have a great day. Good afternoon, good night. Yeah, the thing is, sometimes this is like the old data that I still really have, and then like Obsidian is for more locals. Yeah, you know what? So I like to try different stuff, okay? Because it's nice trying new stuff. I like experimenting and doing different things. Okay, see you guys tomorrow or in 2 days or something. Have a great race. Have a great night. And yeah, I hope everyone can also get a job. Thank you, Alfie, for the amazing server. I still haven't. Yeah, I still don't know like how you sound. By the way, I really don't know what like what. Yeah. Okay. Sorry. I'll see you guys.